For this sections, we're going to talk about limits at infinity and horizontal asymptote. Recall 2.3, we talk about vertical asymptote. So horizontal asymptote is something completely different. Last time we talked about a limit of a function as x approaches to some number equals to infinity. However, this time we talk about limits at infinity, pretty much when x becomes large, like this function right here. So what happened to the function when x becomes large, positive or negative? You see f of x go from -1, 0, and then 0.6, and then approaching 1. So you see right here, this line right here, that's what we call horizontal asymptote. And then we have the definition down here. So the line L is called horizontal asymptote if the curve y equals f of x, if either we have the limit as x approaches infinity, f of x equals L, or the limit of f of x at x approaches negative infinity equals to some number L. All right, so for example, let's take a look at the arctangent. So the limit as x approaches to negative infinity, the limit is going to be negative pi over 2. Or if you go for x approaches positive infinity, the limit is going to be pi over 2. So if you remember the graph of the arctangent function, then you will understand the horizontal asymptote. This is the graph. So this line right here and this line right here, this one is pi over 2 and this one is negative pi over 2. And in fact, those two are the limit. So you see it's approaching, the function is approaching that line, and approaching this line when x approaches to negative infinity. So as you can see, those two lines are the horizontal asymptote for the arctangent function. Now, let's take a look at our current example. We want to find the limit of 1 over x as x approaches infinity, and same function when x approaches negative infinity. Now, if you look at the graph, you see right here, when x approaches infinity, what happened here? You see it's approaching 0. Same thing when x approaches negative infinity. The function is approaching 0. So clearly the limit is going to be 0 for both. So the limit of this function, 1 over x, is going to be 0 as x approaches to positive infinity or negative infinity. That's when you look at the graph. But if you want to plug in some point, it's going to be obvious as well. So for example, you see if I have 1 divided by 100, that's 0.01. If I have 1 over 10,000, it's going to be 0.0001. And then you see that if the number in the denominator becomes large, it's going to result in 0. So it's going to get, the number is going to get smaller as the denominator gets larger and larger and larger. So this is a rational function. So we have a property here. So if r is a positive number and it's a rational number, then the limit of 1 over x to the r as x approaches to infinity is going to be 0. Okay, so keep that in mind when you work out any problems for rational function. So let's take a look at that example we want to evaluate. Now, please never substitute the infinity into x. We're not allowed to do that because infinity is not a number. So please do not do that. Now, to evaluate the limit at infinity, we first divide both numerator and denominator by the highest power of x that occurs in the denominator right here. So you see the highest exponents is x cubed in the denominator. So we're going to use that and divide everything by x cubed. So I have the limit x goes to infinity, and I divide everything by x cubed. 6x squared over x cubed minus 2 over x cubed. So we divide top and bottom by that. Over x cubed minus 4x over x cubed plus 3 over x cubed. Now we want to simplify it before we take the limit. So I ended up with 4 plus 6 over x minus 2 over x cubed, everything over 2 minus 4 over x squared plus 3 over x cubed. And from the previous theorem, we know that this is a rational function, so it's going to go to 0 as x goes to infinity. This one approaches 0. This one approaches 0, and this one approaches 0. So we ended up with 4 over 2, which is 2, and that's going to be the limit.